thanking the organizers for inviting me at this very interesting conference, and also acknowledging my several collaborators who took part in these works. First of all, Mike Hayes, who has played a central role in all what I will talk about. Also, Elsens Jung and Etienne Fodor, who is actually here, and Fernando Caballero, who is a PhD student with Mike. So, what I'm going to talk about is active matter, and I will talk about everywhere, having in mind systems that are at the micrometer scale, let's say everywhere except in one slide, actually. And so I will have in mind systems composed of bacteria or algae, or artificial ones such as autophoretic colloids that we are nowadays able to engineer. I cannot understand whether you can hear me well or not, actually. Great, thank you very much. So, however, this talk is going to be a very theoretical, well, a rather theoretical talk, and focused on minimal systems of active matter. So, in this sense, there will be no space in my talk for the very interesting topics of hydrodynamic interactions and aligning interactions, and somehow the simplest system of, the simplest active system I have in mind is just one particle that is moving stochastically, but whose velocity v is correlated in time with a characteristic time scale tau. So it turns out that if you coarse grain this system and you just look at what happens at time scales that are much longer than tau and length scales much longer than the run length, you only observe a simple Brownian motion. However, of course, active matter breaks time reversal symmetry, and I want to spend a few seconds, a few minutes, to let you understand precisely what I mean by this. Because I think that when I say active matter breaks time reversal symmetry, the first thing that most of you will think about is that active particles are able to transform fuel into motion, and so, of course, motion is not transformed into fuel, and so time reversal symmetry is broken. And actually, this is not at all the kind of time reversal symmetry I want to look at. And in order to make this point as clear as possible, with the danger of being a bit pedantic, say, let me consider two rather peculiar active particles that are given by a Ferrari and an old car. So if the drivers of these two cars want to go to the supermarket, they will soon discover that the fuel consumption is extremely different. So why I'm saying this? I'm saying this because, of course, in an active system, there are two sources of time reversal symmetry breakdown. One is given by transforming fuel into motion and is highly system dependent. And somehow what I want to do is to look at an intrinsic time reversal symmetry breaking that is only due to the fact that active particles move persistently in some direction. So what do I mean by this? Well, the key point is interactions. So suppose you have an active particle that on its natural way finds an obstacle. So what it will do is that it will typically follow this red way. But in the time reversal world, it will actually go straight. So the two trajectories that it will typically follow are different, and time reversal symmetry is broken. And the same thing happens if you look at the effect of interactions among particles. So, for example, if you have two particles that perform a head-to-head collision, then they have to wait a long time in order to rotate and resolve it, while in the time reverse world, they only need a short time to slide past and resolve the collision. So the talk is organized as follows. In the first part, I will talk about the physical implication of this time reversal symmetry. In particular, talking about incomplete phase separation. And in the second part of the talk, I will discuss if and how we can quantify this time reversal symmetry. Okay, so the first implication of broken TRS is the so-called motility-induced phase separation, as discussed long ago by Julien Taillère and Mike Cates, which is the fact that active systems, even if they are, if the particles are poorly repulsive, tend to phase separate in dense-like and dilute-like regions. So is, of course, a non-equilibrium phenomena that is due to what I was saying before. And it can be understood, and it has been first understood, surprisingly, through a mapping to an effective equilibrium system. So let me explain in a little detail how it works. So the idea is that you start instead of starting from a system with two-body interaction, you say, well, the net effect of pairwise interactions is just to create a density-dependent speed of particles, which typically goes down when the density goes up. So if you accept this starting point, then these are the equations of motion that we have. U is the self-propulsion. And actually, by the way, this kind of, this explicit effect on the self-propulsion that goes down with the density is backed by first principle approaches as developed by Thomas Beck here a few years ago. Or this model can also be seen, if you wish, as quorum sensing active particles, meaning particles that are able to adapt their velocity to the density due to some chemical signal of the others. Anyway, if you accept this starting point, getting to a description of MIPS is rather simple. So the idea is that you first take the limit of small persistence time, and then you can, in this limit, you can eliminate the velocities from, the self-propulsion from the problem. And then using some standard coarse graining technique as developed by Dean a few years ago, you get to the surprise that the coarse grained equations of motion are actually in an effective equilibrium. And in particular, this is the free energy that you obtain, which has the interesting property that if the velocity goes down with the density, then it's non-concave. And you know that an equilibrium system with non-concave free energy and conserved order parameter undergoes a liquid-gas phase transition, and this is somehow has been our first understanding of MIPS. Now, this theory is very simple and beautiful. It has the little problem that often in experiments, it's not what is seen. And what is typically seen, this is an experiment by Jeremiah Palacci in Science in 2013, is that indeed particles do aggregate and form clusters, but these clusters are highly dynamical and they do not coarsen to the full system size to a unique blob. So this kind of micro-phase separation or incomplete phase separation has been, there have been several attempts to explain it, essentially by complicating the interactions that are at play, by introducing hydrodynamics, chemiotaxis, birth and death, etc. And I'm pretty sure that all of this is highly relevant if you want to get quantitative predictions. What I want to convince you about is that this kind of microphase separation is a very natural phenomena as soon as you look at the problem from coarse-grained point of view. And secondly, that it's related to another phenomena, which I will call bubbly phase separation. It's known in literature, but somehow vastly overlooked. So at this point, you will probably not be surprised that my kind of starting point is going to be model B of equilibrium liquid-gas phase separation, where phi is the density field, J is the current, mu is the chemical potential that comes from a free energy, and the noise as variance D. And as all of you know, the equilibria of the two phases are given by a common tangent construction in an equilibrium Lie picture. So what I will call scalar active field theories are minimal modification of model B that allow for for breakdown of time reversal symmetry breaking terms in the same spirit as Sriram was discussing a few hours ago. And in order to do so, you soon realize that it's necessary to go at higher order in gradients, and that there are only two ways in which you can do that. The first one is to assume that the chemical potential does not come from a free energy, but there is also another way, which is that you put a current that is not Carl-free. And at lowest ordering gradients, there are only two terms that can do the job. The first one is this lambda term that I will call active model B, and the second one is this zeta term that I will call active model B plus, in lack of a better name. But if you have suggestions, they are welcome. Good. Active model B has been already studied, mainly by Rafael Witkowski and collaborators a few years ago. And I will be back to this model a little bit later on. For the moment, let me only say that from physical point of view, the main effect of this non-equilibrium term is just to shift the common tangents construction that you have at equilibrium to an uncommon one, in which so in the two phases, the chemical potential is equal, but the pressure is not. And and indeed, in simulations of active Brownian particles, this has been explicitly found, and actually a model of this kind can even reproduce nearly quantitatively the densities of the two phases. But what I want to talk more about for the moment is what we call active model B+. That is, we have a current that is not Carl-free. So what does this mean? It means that if you have a modulation in the density, okay, you are able to create a current in the system, which is not possible if the current is the gradient of something. Now, before going to discuss the physics of this model, a rather natural question is whether we can obtain it from any microscopic model of active matter. Yeah. So I'll go exactly to that. So of course you can, but so you can have even in equilibrium at microscopic level a current that is not Carl-free, but what you cannot have in equilibrium is a current divided by the variance of the noise that is Carl non-free. So let me show you. So the idea is that you start from, the idea is to start from this kind of model where the interpretation is somehow similar in spirit to liquid state theory. So the idea is that, if you have interacting particles that are interacting pairwise, you treat the R-core part of interaction phenomenologically by putting it in a density-dependent swimming speed, and you retain the tails of the interaction explicitly in U. Or, differently, you can see this model as quorum sensing particles that are not only interacting through quorum sensing, but, for example, also through excluded volume. And if you do explicit coarse graining with these standard techniques by Dean, etc., and you do, which amounts essentially to write an equation for the empirical measure that is the sum of the delta of the position, and then you do a gradient expansion, so you assume that the density doesn't vary so much, and then you confuse the empirical density with the true density, what you end up is this model here, which is very close by to the active model B or B plus that I was talking about. Sorry, active model B plus I was talking about, except that we have a non-unitary mobility. So we are actually working on understanding the effect of this non-unitary mobility, but I have no final result to present you today about this. And for the moment, I will only present you results in which the mobility is set to be constant. So there is a very interesting outcome of this coarse graining, which is that this activity parameter has a definite sign that only depends on a very simple property, which is whether the tails of the interaction among particles are attractive or repulsive. And please keep in mind this point, because I will be back on this afterwards. So what's the physics of active model B? So this is essentially the phase diagram. At zeta equal to 0, you have the equilibrium model B, dilute phase, dense phase, and between the binodals, which are the red lines, you have a phase-separated system. You switch on a little bit of activity, it doesn't change anything, or it doesn't change much, let's say, but you have a threshold, and above this threshold, either you completely destroy phase separation, or you make kind of a phase separation between a dilute phase and a bubbly phase. So a dense phase that contains bubbles. The dynamics of these bubbles, and for the moment I will only consider this state, this bubbly phase separation. And the dynamics of this bubble is very interesting, because what happens is that bubbles are nucleated in the dense phase, they grow, and they do not, they are not destroyed by antinucleation, but they are destroyed by either merging with other bubbles or by ejection to the dilute phase. So here it's kind of, well, here it's a movie of this phase. You can see the dynamics I was talking about. And actually, what is, in my opinion, very interesting is that this is already seen in simulations of particle models, of particles, of active particles, when the interaction potential is purely repulsive. And this is one of them, which is a work by Joachim Stenhammar and collaborators. So of course we don't get it quantitatively, but we are not meant to, but we get the principle correct. So the model is actually invariant under zeta in minus zeta and phi in minus phi. And please recall that means that, I mean, in our microscopic derivation, zeta negative means the tails of the interactions to be attractive. And, sorry. And because of this invariance, to get the phase diagram for zeta negative, what you have to only to do is to reflect it, reflect the phase diagram you had before, which means that now, at low density, we find a kind of cluster phase. So I've been lazy, I've not changed the colors. Now dense is dark and dilute is bright. And this kind of cluster phases is indeed exactly what is seen in simulations of active particles with attractive, I mean, our core part and attractive tails. These are simulations performed by Joachim and by Romain, but I mean, the result is kind of not new at a particle level, in the sense that, I mean, there are many other studies in which it has been more or less observed. Now, for who has already seen these things, the fact that we get a cluster phase with clusters of different sizes, it's theoretically a little bit surprising. The reason for that is that in equilibrium, what you have the phenomena of Ostwald Ripening, which means that if, I mean, and it's a very generic phenomena, which means that if you have two bubbles of different size, they have different Laplace pressure inside, and because of diffusion, the small bubble will shrink and will make the larger one grow, and that's exactly the mechanism that leads to full phase separation. So let me give you a little few details. So Ostwald Ripening is a mean field argument. So it's understood in zero noise for these field theories, and essentially amounts to assume that the cluster is in quasi-static equilibrium with the surrounding, except that at infinity it sees a supersaturation, and in terms of this it's possible to give an equation for the evolution of the radius of the bubble, which tells you that when the noise nucleates a bubble that is bigger than a certain critical radius, it grows, and this critical radius depends on the supersaturation. When it is smaller, it shrinks. Now, what I mean is active model B plus, is the zeta term able to kill Ostwald Ripening? So it's not, but it's able to strongly slow it down. So what I mean by this is that the argument can be refollowed in this case very precisely, and essentially you get exactly the same equations with the difference that now the surface tension, I mean the term that, I mean when the surface tension was entering, you now have also an exponential suppression of it. And what does this mean? It means two things. First, that the critical radius is exponentially small in zeta, in the non-equilibrium parameter, in activity. And secondly, that the time scale for coarsening is exponentially long in zeta. This is exactly what we see when we simulate mean field equations. So these are simulations of this initial condition, both for zeta smaller than 0, equal to 0, and different from 0. And you can clearly see that here there are both simulations and analytical predictions. You see that there is a perfect superposition. Another way to interpret these strange dynamics of this model is the fact that small clusters seems to be stable is to ask what is the outer density at which a cluster of a given radius is in equilibrium with. And if you do so, you discover that again, the density as in equilibrium goes down, both the inner density and the outer density goes down as one of the radius of the bubble. I mean, the density minus the Van Noordel value goes down as 1 over the radius, but the outer density is actually again, the difference in the outer density is actually again exponentially suppressed. Now, a little few more data on this model, because what does it happen when you switch on noise is that, as I was saying before, Ostwald Ripening is a mean field phenomena. And what does it happen when you switch on noise? We have seen that we go to this cluster of Bubbly phase, but why this happens? So we don't have so far an extremely precise analytical argument, but we have a qualitative one. The idea is that, the time for coarsening is made exponentially long in zeta. So as soon as you switch a little bit of the noise, you will be able to make the nucleation time scale similar to the coarsening time scale. And when this happens, of course, it does not make any sense anymore to talk about Ostwald Ripening. And this simple argument leads you to the conclusion that the critical value above which you enter in the bubble or cluster phase goes up with the noise as 1 over the noise strength. Okay, there are a few more data. For example, you can see that in the bubble cluster phase, of course, you have a well-defined average density of bubbles, but I will skip these things now. So, with Fernando, we tried to approach these models from renormalization group point of view, which would essentially mean, to try to understand what does it happen in this system when you are close to the criticality, so essentially close to these points at long time and spatial scales. And if there is anyone among you expert in the normalization group here, I think the first thing you will tell me is, well, both of these terms are irrelevant from mean field, from dimensional analysis. So that's correct, but there are surprises. In the sense that if you do, and this is what Fernando did, a one loop expansion and you extrapolate it in 3 dimensions, what you discover is that the lambda term, the one of active model B, indeed flows to 0 as expected naively, but the flow of the zeta term is, at the moment, is very different. In particular, what does it happen, this is the RG flow, is that, of course, you remain with the Gaussian and the Wilson-Fisher fixed points, but zeta creates other 2 fixed points that are unstable and beyond which the system the flow diverges. So that's a very similar structure to what happens in KBZ equation in dimension between 2 and 4, and lead us to wonder whether there is a strong coupling fixed point in this model, which is, however, at the moment only work in progress, and I cannot state anything precisely about it. So I will now switch to the second part of the talk, and in particular which will be about measuring, if and how we can measure violation of this time reversal symmetry breakdown that I called intrinsic before. So again, as Seifert has very nicely explained in this talk, the entropy production is a quantity that strongly depends on which system, on which degrees of freedom you decide to retain in the description of your system. However, in this talk, a little bit later on, we will see a little bit of universality. Yes. And a remark that I have is that I will only talk about average entropy production and never about fluctuations of entropy production. So the first model that I want to talk about is work that is pretty recent, is only partially published, and that has been mainly done by Etienne. You can also see his poster if and concern active Ornstein-Uhlenbeck particles, that is this model here, where you have velocities that are Gaussian random variables, and they are exponentially correlated in time. So a very nice property of this model is that you can measure, you can calculate perturbatively the stationary measure of the system in the limit of small persistence time. And this led us to some exact computation in this model. But it is not what I want to talk about today. What I want to talk about today is entropy production. And in particular, this can be rather easily obtained through standard field theoretical techniques by observing essentially that positions are even and velocities, the full velocities are odd under time reversal. And so what you get is that this is the expression of the entropy production, which, however, being a global quantity for an extended system does not, at least for me, does not give me so much information. However, what is interesting is that as soon as the interaction potential is short-ranged, you can coarse grain this guy. And what do I mean by this? Well, I mean that I will denote by S of R the entropy that is produced in a box of size L, of size L by L, which is centered in some points, taking care that L is actually much bigger than the interaction range. And if you do so, well, we did so in Etienne did so in a system that is phase separated. What you see is that there is a very clear signal. This is the entropy production and the density as a function of the distance from the center of the cluster. You see that there is a very clear signal of entropy production at the interface, while entropy production away from interfaces is rather small, a little bit higher inside. So the same thing can be actually found at the level of field theories, and in particular active model B. So again, you can look at this model that shows phase separation. We believe it's the minimal model. It's one of the minimal models for phase separation in active systems. And that's a snapshot of the density profile. And again, if you measure the entropy, what you get is this clear signal at the interface, or as we were saying before, as a function of this of the distance from the center. So this is for me non-trivial because, as we were saying before, entropy production should strongly depend on which degrees of freedom we have retained in the description. And in the particle model, the degrees of freedom were positions. Here is the density field, and there is no a priori reason to get similar results. Okay, so it's most of the entropy is produced at the interface. It's not that in the bulk phases there is no entropy production. Of course there is, but there is a clear difference, meaning that at the interface the entropy production is order 1 when the noise is small, and in the bulk phases is going proportional to the noise to 0. So there is a last thing I want to tell you about, which is essentially this kind of local decomposition of the entropy production is, in my opinion, natural for extended system as soon as you have a system with a spatial structure. But if your system is homogeneous, of course, this local decomposition tells you nothing. So in case of homogeneous systems, what we did was to generalize, to try to analyze entropy production was to generalize some relation first discovered by Harada-Sasa a few years ago, which amounts to connect the entropy production to the violation of the fluctuation dissipation theorem in Fourier space. So K is the wavelength, omega is the frequency, C is the 2-point correlation function of the density field, and R is actually the response to the perturbation of the chemical potential. And we measure this in simulations. You see this is a map as a function. Sorry, here is frequency, here is wavelength, wave number. You see a spatial structure that is non-trivial and definitely different from the one that you get from effective temperature. So I will conclude here, and a part of what I was telling to you about is currently in preparation. We are writing the manuscripts, and I thank you very much for your attention.
Very nice. Can you go back to the last slide, because I didn't fully get your conclusion. Are you saying that the Harada-Sasa is useful and an effective temperature is not, or what is? You were a little bit fast when you explained this slide.
I'm not sure I want to do this hard claim, actually, because I don't know. In the sense that, what is clear is that if we have a quantitative link between entropy production and this quantity.
Yes.
And this adds a structure in Fourier space, which is not the same as the structure that effective temperature has. And I don't want to say more because I don't know.
Mm-hmm. Okay.
You showed the phase diagram for this model as a function of density and this zeta parameter that quantifies like the curl of the. What's with the speed? There's like still as a parameter the speed of particles, right?
Sorry, what about?
The speed, the bare speed of the particles.
So we have not yet connected this phase diagram quantitatively to microscopic parameters. So it's not trivial how the bare speed of the particle system that I coarse grain to go there is actually entering in all the parameters of this model.
Okay,
if I vary the speed, I might cross the phase diagram in a non-trivial way. So, and I agree, it's an interesting question.
So when you say that it is incomplete phase separation, but have you checked the system size effect, that how cluster grows with system size or something?
Yeah, sure. We have checked that we are
that it does not grow with system size, or
no. The typical size of these bubbles or clusters is not dependent on the system size.
It's finite.
Sorry?
It's finite.
It's finite. As it is, as the density of the bubbles in these or clusters in this phase is well defined, so meaning the number of bubbles divided by the volume goes to a constant, etc.
But have you checked the structure factor also? No.